In this video, we're simply going to discuss CHEM1000 Test 1 for the year 2024. So as you are preparing for your 2025 Test 1, please be careful on the topics that you're going to focus on in this video, because the coverage they had last year is not similar to the one that you have this year. So topics like equilibrium, electrochemistry and thermochemistry, if you see such questions that we're going to do here, you can just skip them, focus on the ones that you're interested in. And don't forget to change your video quality to HD, because the PDF were pictures that were just scanned, so they're a bit blurry, so that you're able to see the questions clearly. These are the instructions on your assessment, and we are always going to be given constants. So these are the constants that we'll be needing, and the periodic table is given at the end. So when you're attempting the test, when they give you the question paper, make sure to pull out the tutorial sheet from the end so that it's easy. Instead of you flipping the pages back and forth, you can just remove it. They won't disqualify you. It's allowed to remove it so that you see it close by, to avoid wasting time flipping back and forth. Okay, so we're going to start with section A. Now the PDF, since there were pictures, they're a bit jumbled, so I'll try to be moving back and forth for you to be able to follow. So this is our section A. They are saying answer all questions on the answer grid provided. Each question carries 2 marks. So A1, round up a herbicide manufactured by Monsanto has a formula. This, you have seen the formula that has been given. This is the chemical formula that we have. How many moles of the molecules are there in 304.3 grams sample of Roundup? So they've given us the formula so that we're able to get the molar mass. We're able to get the Mr. using this, and also the mass has been given. So this is just going to remind you of your knowledge of mole concept. So question A1, just to show the illustration, the number of moles that we're interested in is the mass over the molar mass, or Mr. So you can just go it like that. The mass has been given to be 0.4, 304.3 grams, and the Mr. according to the formula that we have, which is this is C3H8, then we have nitrogen and oxygen, and there's a P at the end. Let's just see if there's a 5 at oxygen. So on oxygen there's a 5. So now we go to our periodic table to get the Mr., the molar mass for this. We know how we get it. This is phosphorus, so this is just 1 times the Mr. of P. The Mr. of P, which is just a 30.9. So I'll take it to be a 31. I'll take it as a whole number just for the sake of us discussing here. So I'll take it as a 31, but you need to take it as it is. Then oxygen, I'll take it as 16 instead of 15.99. Nitrogen 1, I'll take it to be a 14. That's your nitrogen there, so I'll take it to be a 14. Hydrogen, I'll take it to be a 1. Carbon, I'll take it to be a 12, sorry. Yeah, so this is a 31. This is 5 by 16. So 5 by 16 is giving me 80. Then this is just a 14. Then this is just 8. Then this is just a 36. Summing up everything is simply going to give us, so on my end I'm getting a 169. So I'm simply going to divide here. Number of moles is equal to the 304.3 grams divided by the Mr., which is 169 grams per mole. So the answer may not be accurate or exact with the one that you have on your options, but we'll get something close enough to help us determine the answer. So here I'm getting the moles to be 1.801. This is the number of moles that I'm getting because I was using these fixed values. So if we go back to our question, you see that there's something close to that, and the correct answer here is just going to be B. That's what you have. So I hope that's what you got. So the second one, A2, they're saying there is this sodium carbonate, which is an active ingredient in baking soda. How many grams of oxygen are in 0.42 grams of this? So we're looking for the grams of oxygen in this mass that we have been given. So again, you can pause the video, attempt it first before you see how we're going to do it. So A2, we're given NH carbonate. The mass is 0.42 grams. That's what you have. So the easiest thing to do here is to get the mister for this whole thing so that we know the contribution of oxygen in the whole molecule that you have. There are 3 oxygen atoms, of course, so we can just say this is 3. I'll multiply this by 16. This is 1. I'll multiply this by 12. Hydrogen, this is 1. I'll multiply it by 1. Nitrogen, sodium. Sodium is a 23. I'll put a 23 instead of the 22.9. So I'm using this. This is going to be a 48. This here is going to be, so sorry in case maybe I made a mistake on the previous one. Let's say multiply this. Okay, this was okay. This was 12. So here it's 16. That's a 48. This is a 12. That's a 1. This is a 23. We are summing up everything. So I'm getting an 84 grams per mole. So if this is the mister that we are getting, oxygen is contributing 48, meaning the mass contribution of oxygen. So instead of getting the percentage, I'll just go direct. So the mass of oxygen, how much oxygen is contributing is just 48 over the whole 84. This is grams per mole. This is also grams per mole. We multiply it by 0.42. Then this is simply going to be, so that's a 48 divided by 84. Then multiply the answer by 0.42. So I'm getting a 0.24. This is the mass of oxygen in the sample. So we're getting this from the 84, 48 is for oxygen. So we're getting this. Some people would have gotten the percentage first. What's the percentage of oxygen? So here they would have done the 48 over the 84, then times 100%. But then this is time wasting because this is section A. They are not concerned about your working. They just want you to give them the right answer. So that when you get your percentage here, which is just, we're saying 48 divided by 84, that's 57, something like a 57. So this is a 57.14%. So if this is the percentage, then someone will say you get 57 over 1 for over 100 times the 0.42 because the whole thing is out of 100. You multiply this by 57.14 times 0.42, then divide by 100. You still get the same answer, which is still this. Yeah, so however you do it, the outcome has to be this. So our option here is 0.24. So our answer there is B as well. That's number 2. Then A3, they're saying, what mass of 4 atoms of copper in grams? What is the mass of 4 atoms of copper in grams? So, what is the mass of 4 atoms of copper in grams? So you need to make sure you understand the question. They've given us 4 atoms, right? So we know this is our A3. They've given us 4 atoms. We have the number of moles is equal to, we say the number of molecules, the number of moles is also equal to the number of particles given over the Avogadro's constant, right? There's that formula that we have. So number of moles is equal to the number of particles given is 4. The Avogadro's constant is 6.02. Let's look at the one that we are given here. According to this, the Avogadro's constant. So we are using this guy here. So we are having, there's a 2 times 10 to the power 23. So if we divide this, so 4 divided by, open brackets, 6.022. So try to punch what we are saying or what I'm dictating so that you see if you're able to get the same thing. So the moles here are 6 point this. So we are having 11524 times 10 to the power negative 24. So these are the moles in the 4 atoms, right? Yeah. So if these are the moles, then we know copper, according to our periodic table, copper has what? A 63.546. Yeah, so the mister of copper is 63.456. This is the mister. So the mass is just going to be equal to the number of moles times the meter. So the number of moles has been given there. That's a 6.6 times 10 to the power negative 24. Multiply the answer you got by the meter of iron, which is this guy here, if I'm not mistaken. Yeah, that's 546. I mean, that's 5. There's the 5 is coming first. So 546. So you're multiplying this by 63.546. So the answer I'm getting, the mass that I'm getting, is simply a 4.22 times 10 to the power negative 22 grams. That's the mass that I'm getting. So the answer here has to be, according to this, the answer which is close to the one that we have. So according to the answer that we are getting, there is no proper option. So I'm certain this was corrected during the assessment, during the test. Obviously, someone raised their hand, they couldn't get the answer, and obviously they took note of it. So the closest to the answer that we've gotten is simply this. So you put the closest. By closest, you look at the number you've gotten. The answer we are getting is 4.22 times 10 to the power negative 22. Unless if I'm punching this wrongly, but this is what you're supposed to get. So this should make sense to you why we're saying there is no correct answer here, because we simply used 1 mole of particles always contains 6.022 times 10 to the power 23. So these are atoms. The question says atoms. So how many moles are in 4 atoms? That's what we basically did. So this here will give you an answer to be something like a 6 point something times 10 to the power negative, I think 20. This is we're dividing. So the answer is this. Then we're dividing it. So this is... yeah, my answer here was 6.64, the moles, times 10 to the power negative 24. Yeah, so this is a 10. These are the moles that I got from here when you cross multiply the value of x. So now we know number of moles is mass over meter. So we're looking for mass, so we'll multiply the number of moles and the meter. That's the reason why we are multiplying this number of moles and the meter of copper, which is 63.546. And the answer that we are getting is a 4.22 times 10 to the power negative 22. So the closest to this, that's why I'm saying the nearest is simply going to be your C, because all these are very big, right? Yeah, so this is going to be our answer there. In short, there was no correct answer on C. The question was erroneous. So number A4, they are saying the manganese permanganate ion is often used to analyze the ion, yeah, so ion with a balance of 2 content of an aqueous solution via the reaction. So this is the reaction. What is the ratio of ion to permanganate in the balanced equation, right? So the key here is to first of all balance the equation, and if we are balancing this equation, we're going to use the ion electron method. Or you can do it in any way, whether acidic or basic, but just saying balance the equation first, then check the integers in front of the manganese and the ion. So to do that, I'll rewrite this equation separately. Okay, so this is our equation here. That's on question A4. Now we're going to balance this to get the ratio of what we're interested in. So first of all, split this, and we're simply going to write everything else except hydrogen. So this is going to be equated to the manganese, this guy here. And the next one will simply be the ion. This is 2 plus, changing to become ion. This is 3 plus. So ignore anything else that is not unique. By unique, I mean ignore this and ignore that. So just write this to be equal to that, and also write this guy is equal to that. So these are the 2 equations that we are getting. Now, after you split them like this, you balance oxygen using water. So the side that is lacking oxygen, so this first equation is the only equation that has oxygen. So we are going to balance oxygen using 4 water molecules, because we balance oxygen using water. And once you introduce the water here, you have also introduced hydrogen ions, which are 8 in this case. So we are going to have this. So hydrogen is balanced. There are 8 this side and 8 the other side. Here, the only thing we have to balance are electrons. So put a single electron this side. Because the charge here is 2, the charge there is 3. So 3 minus 2 is 1. We put the difference as the number of electrons on the side that has a bigger charge, which was +3. So that's a single electron you are seeing this side. Then here, the charges are +8 and a -1. The charges here is 0 and +2, meaning this will just be a +7 and this will be a +2. The difference here is 5. That's a difference. So meaning we'll add that as the number of electrons on the side that has the bigger charge, which is this side. So I'm going to add 5 electrons this side because electrons are negatively charged. So if you are confused with this, right here on the channel there is a video on balancing redox equations, so you can check it out. It will help you understand what we're doing here. So this now is going to be hydrogen plus the permanganate ion plus 5 electrons. This is giving us 4 water molecules. So the reason why we added 4 on water is because a water molecule only contains 1 oxygen and we have 4 oxygen atoms this side. So to balance it, no wonder we have to introduce 4 water molecules. Then this guy here has no oxygen, no hydrogen, so we are only balancing electrons, which we have done so by putting an electron this side. I mean, we balance the charges using electrons. So if you see the number of electrons here is 5, the number of electrons here is 1, so I'll multiply this equation by 5. This is going to be 5 like that. The main idea is that when we combine these two, the number of electrons have to cancel because they're on opposite sides. Maybe if you may see it, if I put it like this, 5 ion, 2 plus, to give us 5, F3 plus, then you have 5 electrons. So this is how this is cancelling. And right here, we can now write the final balanced equation. This is just going to be H hydrogen ions plus the permanganate negative plus 5 ion 2 plus to give us, this is 4 water molecules plus the manganese 2 plus 5 F3 plus positive. They want the charge between ion 2 and the permanganate. So ion 2, so if we go back here, ion 2 is 5, the permanganate is 1, so the ratio is 1 to 5, or rather we can just say 5 to 1 because they started with F2, right? Then the permanganate is this side. Yeah, so this is 5 to 1. That's going to be our answer. So our answer there is option D. That's going to be your answer. Then your number A5, they're simply telling us that a given mass of a gas in a rigid container is heated from 100 to 500 degrees Celsius. Which of the following responses best describes what will happen to the pressure of the gas? In short, they're just asking us the relation between pressure and temperature. You can use the ideal gas equation to recall that pressure is directly proportional to temperature, or rather you can say something like this: P1 V1 is equal to P2 V2. Now you know that there is T1 and there is T2. So this here they're simply saying what will happen to the pressure, right? It's a gas, so you are heating a gas. What happens to the molecules in a gas? They become fast, they become more random, right? They move very fast. So meaning the pressure is going to increase. That's the reason why they'll be moving very fast, because they're being heated up. They now have kinetic energy. Yeah, so they're saying the difference here is what? The difference here is 400. That's a main that's a difference, right? Because we were saying a given mass of this container is. So now let's take this. I want you to see by what factor we mean here. When they say with what factor, you give yourself numbers here. So we are on A5. So imagine the initial pressure was 2 now let me give you something that you'll be able to visualize easily. Let's say it was 10 atm. So the initial pressure is 10 atm. The initial temperature is 100 degrees Celsius. Volume is being kept constant. Let's assume that. What will be the pressure at 500, right? So now you will notice that if we multiply, that's going to be 5,000 is equal to 100x. So meaning we divide by 100, divide by 100. So this 100, x is equal to what? 50. So meaning what has happened to the pressure? It has increased by a factor of 5, right? So the correct answer here is going to be B. So the correct answer is B. So you can just use those arbitrary numbers to make the options make sense to you. Yeah. Then number 6, A6, they're saying a gas exceeds a pressure of 1 atm at STP. So what are the conditions at STP? STP, we know one mole occupies what? They occupies, is it 22.4 liters? That's at STP. We can just go back here to try to verify here. This is what we are okay. We're given this condition here to say the temperature also at STP at this. They should have added to say 1 mole also occupies this volume. This will be 4 liters. Then at RTP to be 24 liters. Yeah, so that should be on your fingertips. So now they're asking us to say, what must the temperature be adjusted to for the gas to exceed a pressure of 4 atm? Give your answer in degrees Celsius, right? That's what they want. So we have our question. Let me just write the data this side. This is A6. So sometimes chemistry is like physics. For you to know what to do or the formula to use, you have to write out all the data that has been given in a question. So they are saying at STP, we know first and foremost that 1 mole is equal to 22.4 liters. This is what is happening at STP. That's what we know. Then they are saying a gas exceeds a pressure of 1 atm. So the pressure has been given, 1 atm. At STP, so with these other conditions there, right? That's what they've told us. Then they're telling us that what must the temperature be adjusted for the gas to exit a pressure of, the new pressure is what? The new pressure is now going to be 4 atm, right? That's what they want. So at STP, we're starting with these conditions. So I'll try to use this equation here. I'll put this equation there. So here you're able to see that at STP, the temperature is supposed to be 273.15 in kelvins. Now this is equivalent to 0 degrees Celsius, right? That's what we just have to use. So we know to say, according to our working here, we are having the pressure is 1 atm. So we'll just say the pressure is 1 atm. So I'll try to use this equation. The temperature there is equal to P2V2 then over T2. So firstly, the pressure is 1 atm and the volume is given to be 22. So this is going to be, we can keep the volume to be constant. So this is 22.4 liters. The initial temperature is 273. The final pressure is going to be 4. This is 22. It's still at STP, so the volume is still the same. But the pressure has changed. So what will be the temperature now? So if we're looking for this, this is going to be, this can cancel first and foremost, meaning, okay, the T2 is just equal to 273.15 multiplying a 4. That's what we are having. So this is 1092. This is in kelvins. So now we know to convert something to kelvins, we always say we add the degrees that you have in, and the temperature you have in degrees Celsius plus a 273, right? So now we have it in kelvins, we need it in degrees Celsius, so just subtract. This will just be the temperature in kelvins minus 273 point that. So when you deduct here 273.15, so the answer is 819. This is going to be 819, so the answer is going to be that in degrees Celsius. That's what they wanted. That's your A6. Then now we are moving to A7. A7, they are saying, what volume of methane at 0 degrees Celsius and 1 atm contains the same number of molecules, meaning the same number of moles as 0.5 liters of nitrogen measured at 25 to this? What is the volume? What volume of this contains the same number of this at these conditions? The same thing here. To understand the question, you should be able to write the data separately. So we're on A7 now. So write the information separately. We are given CH4. That's what we have. Then they're saying the temperature for this guy is 0 degrees Celsius. And the pressure is 1 atm. then they are saying what volume of this, right, will be needed to occupy the same number of molecules as compared to nitrogen, with 0.5 liters as the volume, measured at 27. So the temperature here is 27 degrees Celsius, and the pressure here is simply 1.5 atm. They're saying what volume, right? We're looking for volume of this will exist at this if it will have the same number of molecules as compared to the nitrogen. So now, according to our nitrogen, we can just formulate the equation here, because they're saying, that's what we're having. So according to this, we're simply going to write PV is equal to nRT. So the pressure we have is 1.5, right? That's what you have. 0.5 we have. The number of moles we don't have. R we do have because the temperature is in kelvins, so meaning R that we're going to use the universal gas constant that we're going to, the pressure is in atm, so we're going to use this constant there, 0.08206. Then multiplying the temperature has to be in kelvins. So this is 27. We are having a 273.15 plus 27. That's going to give us a 300. So I'm having 1.5, 0.5 liters. Number of moles, 0.08206. Then multiplying 300.15. Then we are dividing here 206 and 30015. So in your working, when you are solving this in an assessment, in your test, please make sure that you don't round off midway through your calculations. Don't round off. And also, only, so this is there's 300 as well here. Only round off if it's a final answer. And also don't forget to show the units. All the units must be shown. So I was supposed to write ATM there. I was supposed to show my liters there. I was supposed to show the units of the R, the units of my temperature. So everything was supposed to be indicated. So there's 1.5 multiplying 0.5, which is our volume there. So the answer there is 0.75. I'm going to do this slowly in parts. The down part is a 300.15 multiplying 0.06206, so that we don't make a mistake. This is going to give me a 24, then 63. This now is going to give me this times 0.75. This now is giving me 0.03045 0287. These are the moles that we are getting. Now they said they have the same number of particles or the molecules, so I mean they have the same number of moles. Now we're going to go back to our methane or CH4. We're looking for what they're saying, what volume, right? So PV is equal to nRT, meaning the volume is equal to the number of moles that you got here times the universal gas constant there, which is simply 0.08206. The temperature, they're saying at STP, the temperature is 273.15. That's what you have. Then the pressure that we are having at 1A this is 1 atm. Yeah, so the volume is just going to be this times 0.08206, then times 273.15. So the answer I'm getting here is 0.68 liters. So rounding it off will be 0.7 liters. Yeah, so this is what we're getting to be our answer. So it was 0.68. So our answer is simply B as well here. That's your option. That's your B. Then the next one, A8, they're saying Avogadro stated that equal volumes of gases under the same conditions of temperature and pressure have equal. So equal volume, so when the volumes are the same, right? So when the volumes are the same, meaning P1 over V1, over T1 is equal to P2 over T2. So when volume is constant, so this guy came up with the idea that whenever the volume is constant, under the same conditions, so we're saying equal volumes of gases under the same conditions of temperature and pressure, when we standardize everything, we're going to simply have, they're saying pressure have equal, there should be equal number of moles, equal number of this. So the answer is simply this. It's going to give us equal number of moles. N is going to be constant. So N is actually a constant that depends on PV. Then we have RT. So we have something like this, right? So if you standardize these three, meaning everything, number of moles will be the same because it's only going to be R that is going to be changing. So all these other quantities are held constant. So the correct answer here is A. The moles will be the same. So here now on question number 9. Question number 9 is about orbitals. So you see how the transition has been made. We are coming from more concept. You went to gases. Now you are going to atomic structure. The next will be chemical bonding. So they just follow the order of the topics. Yeah, so you can actually specialize on which topics you're going to focus on if you feel that you have less time to prepare. Because everything is going to be having some questions. So A9, what is the total number of electrons that can be filled in S, P, and D orbitals? So S can only accommodate 2 electrons. So we have option B, C, possible ones. S can have 2, P can only have 6, so we're left with these 2. Then D can only have 10. So the correct answer there will be C. That's what you have. Then number 10, they are saying when the elements in period 2 of the periodic table are considered in succession from left to right in the second period. So if we are here, the period we are discussing about is the second one here should be this one here, if I'm not mistaken. This guy here should be the second period. This is the first. Yeah, so this should be considered. So let me see. In succession from left to right, there is a decrease in atomic radii with increasing atomic number. This can be explained by the fact that, so there is a steady decrease in the atomic radii. So there's a steady way that we're going to see the atomic radii behaving in as much as atomic number is increasing as you move from left to right, because the rings are supposed to be increasing, because you see the number of what there is an increase by 1 electron. So you're seeing 13, 14, 15. So the rings, we're expecting them to be a lot. So if the ring, so like for the first one, you have 2, that's 8, then you have 1. This is 12, so we just have the same number. Then this next one, also we have that. The next one has that, so 14 to still be the same. So you're seeing not really the steady in terms of the shells are the same. The number of shells is still going to be the same as you move from left to right. Now you always observe a steady increase in the atomic radius as you are moving down. It's easy to explain if you're going down because the shells are piling up. Like this has 2 shells, this has 3 shells, and so on and so forth. Yeah, there's a ridiculous increase here in terms of you're seeing the skip from, look at 11, we go to 19, we go to 37, 55, then 87. So this is okay to explain. It's easy to see. Now, with regards to the trends across the period, when we discuss atomic radii, we say that it relatively decreases because of the effective nuclear charge. The pull between the central part and the outermost shell electron gets to be too much, right? Because the more you have electrons this side, the more the electrostatic attraction between the outermost shell electrons and the central part. Why? Because protons on the central part of the atom are positive, and the electrons here in the last shell are negative. So if you continuously increase the electrons in the outermost shell, which is what happens when you're moving from left to right, the attraction becomes stronger, and then the size of the whole all the shells or the rings decrease, making the atomic radius to actually be decreasing slightly. So here are the options. Let's eliminate them. So we're just saying the core charge increases and the added valence electrons shield each other from this charge. So this is force. It's supposed to be opposite. Then B, they're saying the core charge decrease and the added valence electrons do not shield each other from this charge. This is partially true, but let's look for something more suitable. The core charge decreases, that's true. The attraction is going to be, we say it decreases, like here the core charge, the positivity of the central part, the proton is decreasing because we're adding electrons, so electrons are coming to cancel that positivity of the core part, which is the proton number. So the core charge decreases and the added valence electrons shield each other. No, they don't shield each other. If they shield each other, meaning there'll be less interaction. Then D, the core charge increases. So the perfect answer here is actually B. Added valence do not shield each other. The core charge increases. No, the core charge decreases because you're going to have a smaller effective nuclear charge. So according to our understanding, let me explain. Let me show you what we mean by the core charge decreases. Yeah, so let's say you have 2 electrons here, and there's a single electron there. So the charge here, the effective nuclear charge, is equal to, you are going to say, what's the proton number? The proton number is 3 minus how many core electrons do we have to deal with? There are 2. So this is going to give us what? Positive 1. So that's the attraction between the central part with the outermost part. Then imagine if we increase this. There's still 2 electrons there. Then we are still having, let's say I put something like this. There are 8 now. So these are now 8. So the charge of this guy in the outermost shell will be, so this is now having what? This is now having, let's say we have what? We have 11, right? 11 minus, there are 10 charges. So there are 10 electrons that we are countering. Or let's say we are 12, right? 12 minus 10, so the charge will be positive 2. So if I put another electron there, meaning we're having what? The charge is what? The charge, it was now 13. 13 minus 10. Look at what we're having. Yeah, so the attraction actually, the effective nuclear charge, so this, I think we explain it. Yeah, so this will make us choose, so the answer here is what? The answer here is D. Yes, that's a perfect answer. So point of correction here, the core charge increases and the added valence electrons do not shield each other because we're adding them in the last shell. They're not shielding each other in terms of, we're not adding them in the shells in between. Like these 10 electrons you are seeing here, the first 2 and the 8 electrons here, they are shielding, they are hiding, or rather preventing the central part from having a direct interaction with the outermost shell electron. So this is the pulling effect. That's what we're calling the core charge. So the core charge is going to be increasing because from left to right, the proton number is increasing. So meaning the charge is supposed to be increasing, and these guys do not shield each other. Everything in the outermost shell want to interact with the central part. So they do not challenge each other. They will actually be far apart from each other and try to be attracted to the central part. Yeah, so hope that makes a bit of some sense. Then here we have A11. So A11, they're saying the uncertainty in measuring velocity of a particle is 400 and its mass is that. Calculate the minimum uncertainty involved in measuring the position of this thing here. So here we're simply going to use the uncertainty principle, the formula that we rarely talk about, but it's there in physics. You discuss it here in chem partially. So you have A11, this they're saying the uncertainty in position, the uncertainty in velocity is equal to Planck's constant 4 pi. That's the formula for the uncertainty. The velocity is given, so the change in velocity is simply what? 400, right? The Planck's constant is 6 point. I think there should be a mass here something. I'm not sure. Let me just cross check. 2610 to the power negative what? Is it 34? So Planck's constant, this is what you're having. That's okay. This is Joule's second. That's what you're having. So now down here we just have 4 by pi, which is 22/7. So the uncertainty, this is uncertainty in position, uncertainty in velocity. Yeah, because it says we cannot determine both the velocity and the position of an object. So this is going to be 400 by 4, then by 22/7. So the mass should have been just a distraction there. So we are having 6.62 times 10 to the power negative 34. So please try to cross-check in your notes if this is the formula for the uncertainty principle formula. You can just search that even on Google to see what it's going to give you. Then we are dividing it by 400 by 4, then by pi. So this is just going to give us 1.3. Let's see if we have something matching there. This is very less. They're saying calculator the uncertainty, the minimum uncertainty involved. This is 4,000. Sorry, this is 4,000. Sorry, this is a 4,000. Okay, so we are having 6.626 times 10 to the power negative 34 divided by a 4,000, the velocity times 4, then times pi. So here I'm getting still the same. I'm getting the same to be 1.3 times 10 to the power negative 38. So from here, they're saying the position, the mass. Okay, so the answer I'm getting here is actually correct. So the answer we got was 1.3 something. This is okay, so the answer I got is the final thing I'm getting here is 889 times 10 to the power negative 12. So this is in meters per second, is it? Because here we are going to multiply this by the the mass, which is the mass given there on A9 is 1.67, then times 10 to the power negative 27. So the first answer I got here, the uncertainty, the true answer here is 1.3, then times 10 to the power negative 38. So the units of uncertainty, this delta x, the position is always given as kilograms, then meters. Right, this is what you have, meters per second. So this is meters per second. Now there was mass given, so they divided this by the mass, 1.67 times 10 to the power negative 27 kg, to get rid of the kg, to just leave the answer in meters per second. So this is the answer that they are supposed to give us. But then surprisingly here, I'm shocked why we don't have meters per second. But either ways, the correct answer we're getting here is supposed to give us 7.8. Yeah, so 7.8 times 10 to the power negative 12. So it's close to that. That's the only closest thing we can get. Yeah, so hope you're okay with this. The formula is correct. Yeah, so this is the uncertainty in the position, and the uncertainty in the velocity is always Planck's constant times 4 by pi. Then you also know the formula that's this guy is connected to mass, then times what, times velocity, right? So there's this other formula here where V is on, this is the de Breugler's equation. This is where the whole uncertainty principle came from. Yeah, so that answers your question number A11. Then we're going to A12. They're saying given the wavelength in meters for the electromagnetic radiation in the table below, which of the electromagnetic radiation listed in the table above has a frequency of that and the energy of that? So we're simply going to use the information given. So the frequency has been given. This is your frequency. Your energy is this guy here. So these are wavelengths, right? These are wavelengths in meters. So we're just going to work backwards. Yeah, so don't be overthinking this. This is atomic structure. They're just playing with your formulas. So we know to say energy is the same as Planck's constant, the speed of light over what? Over wavelength. Or rather, we know to say energy is equal to Planck's constant and frequency, right? You also know to say frequency is equal to speed of light over wavelength, right? This is, you know this. So they're asking us which of those guys here in the EMR is corresponding with the energy that we have and the frequency that we have. So we can choose one equation here. So I can just use this. I can just verify by using this. I can just say the wavelength has been given to be 7.5. then times 10 to the power 14. This is per second. The speed of light is 3.00 times 10 to the power 8 meters per second. Then down here we're looking for wavelength. So wavelength is just 3.00 10 to the power 8 divided by 7.5 10 to the power 14. So here now, on the punching, make sure you put the first answer of the numerator in brackets. So 3.00 times 10 to the power 8 in brackets divided by, open brackets, 7.5 by 10 to the power 14, just positive 14. The answer I'm getting is, this is going to be a 4.0. So this is 1, 2, 3, 4, 5, 6, 7. The answer will be like this, times 10 to the power negative 7 meters. This is my option. So the correct answer there is UV. Yeah, so on the thing here, my correct answer is UV. So the answer here is C. Yeah, whichever way you decide to do this, the outcome is still the same. So if you use energy, try to get the frequency, it will still be this frequency, then you can use it to get your wavelength. Yeah, so it's one and the same. The number A13, they are saying this is a chemical formula of ethanol. Which of the following bonds in this compound is the least polar? So we need to write this whole thing in a way that will show the whole molecule so that we determine which one will be the least polar. So we have C2H5, we're on A13. Then we are having oxygen, this guy here. So there is a carbon and another carbon. There are 5 hydrogens. Is it? There's this, there's another guy here, there's that, there's another guy there, there's another guy there. Yeah, so they're saying which of these guys is the least polar. So the least polar here is going to be, let's see the options. The options, there's carbon to carbon, there's carbon to oxygen, oxygen to this. The strongest will be this guy here, oxygen to hydrogen. This will be the strongest. I mean more polar in short, because this is electronegative. Yeah, then the one that will be least polar is the one between carbon and hydrogen. Yeah, because these guys are relatively weak. So this will be the weakest. Because of electronegativity, we're saying electronegativity increases as you move from left to right. Yeah, so, and also up a group. So you see that from the periodic table, only oxygen is the most electronegative one. The rest are relatively not electronegative. Yeah, so in comparison to what we are having, oxygen is more electronegative, followed by nitrogen, then carbon. So carbon and hydrogen, which is far apart this side, are the guys that will be less polar. So the answer here will be A. The number A14, which of the following molecules has a 0 dipole moment? So this guy here, there is carbon, this is this. There are no charges there. Yeah, so let's talk about water has, so there's no 0 here. We don't have a 0 charge because we can get this. There's a chlorine there, a hydrogen and a hydrogen. These guys will pull each other. Then here we're going to have, so the only place where we are unlikely to see it has a 0 net, because this is a linear and we are saying the pull this side is the same as the pull this side. And there are no lone pairs on the carbon, right? So meaning this will experience 0 dipole moment. So the answer there will be 2, because this one here, the pulling by chlorine is different, is not the same size as the pulling by hydrogen. So this you will see the dipole moments forming up. Yeah. So but for carbon dioxide you won't. So the answer there is A. Then A15, they're saying from the table below, identify the compound with the highest ionic character whose, when the electronegativity given are these. So this is what we are having. So this is something that I gave in one of the videos when we were discussing chemical bonding, and also when I was starting to explain the trends of the periodic table when it comes to electronegativity. Yeah, so you are given a box. So a box, there's X, which has electronegativity to be 3. You have Y, which is 2.3. You have M, which is 1.8. Z, which is 3.8. You have V, which is 1.0. You have L, which is 3.1. You have T, which is 3.4. So look at A. We're just going to compare everything there. A is X and L. X and Y. So X and Y, the difference here is just going to be what? 3 minus 2.3, that's going to be 0.7. 3 minus 2.3. So the first one on A, X and Y, the difference in electronegativities is 0.7. We keep it. Number B is M and Y, M and Y. So the difference between 2.3 minus 1.8 is 0.5. So this is 0.5. Then C we're having Z minus V. So Z minus V, that's going to be 2.8. Then D, we're having L minus T. So L minus T, that's going to give us 0.3. The question is asking us, from the table below, identify the compound with the highest ionic character. So the highest ionic character that you're going to see is this one, the one with a big difference. Because we remember we said less than 0.5, the molecule is non-polar. Between 0.5 to 1.7, the molecule is polar and it's a covalent bond. Above 1.7, it's ionic, right? So this is the one that's ionic. So the answer there is C. That's your answer. That's how we do that. The option there is just going to be C. Question A16. The calculated formal charge of carbon in cyanide is, so carbon in cyanide, so the whole complex ion just looks like this. We have, there's a cyanide here. This is your cyanide ion, a complex ion. So we're looking for the formal charge of carbon. The formal charge of carbon will be the valence before it bonds. The bonds, the lone electrons, there are 2, so this is just going to give us a -1. So that's our A16. The valence electrons before carbon bonds, right? That's the 4. Then the number of bonds or lines connected to carbon, there are 1, 2, 3. Then how many electrons are not participating in the bonding that are present on carbon? There are just 2 of them. So that's the formula for formal charge. Valence electrons minus the bonds associated with that atom you're interested in, then the lone electrons that are present. Yeah, this will give you that. Yeah, so I hope this is okay. So the answer there is just going to be, we're getting a -1, so the answer should be A. So the answer here is A. Then number, okay, this is now 16 here. So okay, 17. There was a mismatch in the questions. This is supposed to be 17. Then they're saying, what mass in grams of nickel could be electroplated from a solution of nickel 2 chloride by a current of 0.25 amps flowing for 10 hours? Okay, so this is under electrochemistry. So we're going to have the data here. Let's write the data that we're having. This is question 17. So we are given that we're looking for mass, right? This is nickel. So nickel is simply here having, they're saying there's a 2, right? This is just going to give us, we need 2 electrons for us to form back our nickel solid. So you need to create the equation that talks about the element you're interested in. So with the valence that it is having. So this is the nickel that you're having. We need the number of electrons, because the first thing that we need in the calculation of time. So first of all, the normal map is that we always have our mass. Mass will give you the moles. From the moles, you get the moles of electrons. You multiply. So here you get moles of electrons when you multiply it by the number of electrons that you are given. From the moles, you get the charge. So here you need to get the charge. Why? Because 1 mole of electron is equal to 96500. This is Faraday's constant. Then this will give you the time that was needed, right? This is the time, which is just going to be the charge is equal to current times time, IT. This is what we get. This is the normal roadmap that we use to solve any question that involves electroplating when it comes in electrochemistry. So this is the map that we always use. Now, this question has been phrased in a reverse manner. Time has been given. The time is what? 10 hours, right? So you convert the 10 hours to seconds. You know, to say 1 hour is equal to what? 60 minutes. So we can just convert this. I'll just start with a 10. We can do this at the same time actually. This is 10 hours. We know to say 60 minutes always gives us an hour. Then we know to say 60 seconds gives us 1 minute. I want to cancel the minute, cancel the hour to remain with seconds only. So this is going to give us 3, 6, 1, 2, 3. This is the time that we are having in seconds. So now if we have the time and the current was given, the current is given in the question to be 0.2 amps, 0.25 amps. So we can use it to get the charge because the charge is equal to current times time. So this is 0.25 multiplied by 3600. So we are getting 36000 multiplying 0.25. So according to my calculator, I'm getting a 9,000 columns. So if this is the charge, we know to say every single mole of electron should give us 96,500 columns. According to our data here, we have what? This is supposed to be according to the Faraday's constant. Okay, so here it was 96485. This is what they were using here. So that's what we're going to stick with. So this is supposed to be 96485 columns. Then how many moles of electrons will be present in 9,000 columns? So we're just going back. So meaning we're dividing the 9,000 divided by 96485. This is giving us the moles of electrons is 0.093278747. This is moles of electrons, right? So the moles of electrons divided by the number of electrons that you had, so that the part for electron cancels. So there were 2 electrons. The valence tells us that. So the number of moles now is 0.046639374. This is the number of moles. Now this is nickel. So nickel, this is Ni, somewhere where this is nickel. So we have what should be, isn't it somewhere here? This is Ni, or maybe I'm mistaken. Okay, it's here, 58.69. Yeah, so now that we have the number of moles, we know number of moles is mass over Mr. So the Mr is equal to the mass is equal to number of moles times Mr. Yeah, so the number of moles times the molar mass. So the mass that you are getting divided by 58.69, then 34 to give us the mass. The mass is 2.7. So the answer I'm getting is a 2.7. Yeah, so the answer is simply A. Yeah, so this, I doubt if it's part of your coverage for the 2025 test 1, but this is basically how we do it. If you're in need of the full video for the lesson, the whole topic, there's a separate, just check on the channel under videos, there's electrochemistry. You can see the video where we have this type of, these examples rather. Then number 17, which of the following statements are true for all galvanic cells? So galvanic, this is true under electrochemistry. Galvanic is just a cell where the reaction is spontaneous, and we have the case that we have is something that looks like this. So under galvanic, we're just saying you have your voltmeter here, you have your anode and your cathode. So we do know that this side here you have your anode there, right? This is your anode, this is your cathode. Then where this guy is, that's where oxidation occurs. Then this is reduction. This is what we are having. Reduction always occurs at the cathode, so it goes like this, right? Electrons move from the anode to the cathode. Yeah, so now let's check our options. Reduction occurs at the cathode, that's true. The anode gains mass during discharge, the mass, so this is false. The anode loses because electrons are moving from the anode, they're going to the cathode. Then they're saying the voltage is less than or equal to 0. So this is false because the voltage on the voltmeter has to be positive. It has to be greater than 0. That's what the E cell is supposed to read. That's how you know to say you're dealing with a galvanic cell, because it's self-driven. It's spontaneous. Yeah, so the correct thing here is just 1. Yeah, so the answer there will just be A. Then number 18, they are saying, what is the correct nest equation for this? So the nest equation just simply means we need to deal with the whole expression at non-standard conditions rather. So I'll write to you the nest equation here. So this will be applicable in your test 2 though for you guys this year 2025. So we're having M2 plus. This is 2 electrons. This is giving us M this side. This is solid. Now this is going to be, the next equation says the cell potential is equal to the cell potential at standard conditions. So we say E cell minus 0. Supposed to be 0.591 if I'm not mistaken over N. Then this is log. This is equal to the quotient. We're supposed to be having the product. If there's any ion on the product, so put the product over the reactant. So the reactant, we just need ions, so if there's nothing, we'll put a 1. So that's what you have. Then we know N is 2. N is 2. That's what we are having. N is 2 because the 2 electrons, right? The N is the number of electrons transferred. There was no E cell given. So this is going to be 0.5, okay, 0.0591 divided by 2. The answer is 0.02. So this has changed because, okay, so this has to be, this changes. Yeah, this will be the E cell. So we'll just take it as the E cell because this here will be a 0. Yeah, so the E cell will just be equal to this guy here. So the correct answer there should be what? So this here, we're having everything's 1 over that. That has to be, so we just focus on the one that is, okay, the log 10 is correct. So what we are changing down there is also correct. Then the value of the expression, this number here on top is totally dependent on the temperature given. So I needed to say this is what they say with RT. So we have, let me write it for you here. So here now we're going to use, this is the next equation. So the R is 8.3145. The temperature has to be in kelvins. The temperature given in the question is 45. So we convert it to kelvins. That's going to be, so the total thing, if you punch everything here, because I'm just going to replace a 273 plus 45 to convert it to kelvins. The number of electrons is 2. The Faraday's constant is 96485. Then here you're having a log the product over the reactant, any ion on the product side divided by any ion on the reactant side. So there is no ion on the product side. Not why I'm putting 1. There is no, I mean there is this guy here. So the charge is balanced, everything is balanced. So not why I'm taking this to put it down there. So this is supposed to be your next equation. Yeah, so this has to be negative. We take this side to be positive. So this is supposed to give us, so what I'm getting is 0.0137, then log 1 over M2 plus. So the closest answer to this, from what we have here, we can eliminate which one. This is 13. So this is, we're getting what is the 13. So this has to be 1. What's closest to 1? That's 0.0. So this is close. The closest answer here is this. So the answer here, we're going to take D because it's closest to what I've gotten. Yeah, I'll try to redo this separately, but this is what we're supposed to get. Yeah, so this is supposed to be your answer. And the next equation is really always going to be depending on the information given in the question. No wonder the standardized one, the one I gave at first, has a constant 0.0591. and with just N down because it's always going to be varying. And here down, the reason why I'm picking this is because M here has a positive 2, this This is log 10, so the base is the same. So these two actually are almost the same. Is it the same thing? The difference is where the difference is. They should not have put this notation, but this is okay. No, this is okay. This is okay. So our answer here is D. So please try to watch the full video to get. I gave everything in the other video. So this is what you're going to get. And the next one is the last one there, which is simply A20. This was supposed to be A20. Yeah, so A20 here, they are simply giving us to say which of the following conditions are satisfied when the cell reaction in an electrochemical cell is non-spontaneous. So if it's non-spontaneous, first of all, we know to say if something is spontaneous, its E cell is going to be greater than 0. But the work done Gibbs free energy is negative, NF, then the E cell that you have, right? So if it's spontaneous, meaning this guy is positive, we put it there. So meaning G is going to be less than 0 because E is our only chance of changing or getting rid of this negative. So meaning G has to be less than 0. So the correct answer here will be B. That's what you have. If the reaction is, this is when it's non-spontaneous, so it has to be greater than, because if this is when it's spontaneous, right? In a galvanic cell. In a non-spontaneous case, meaning the E cell is negative, is less than 0, meaning when you put a negative then the negative, it cancels. So G is greater than what? 0. Yeah, so notice the difference. Spontaneous, E is greater than 0, G is less than 0. In a non-spontaneous, E is less than 0, G is greater than 0. Yeah, so our answer here is just going to be A. That's what you get. So that marks the end of section A. Now we can start section B. So now section B here, we are having this part here. They are saying a piece of antimony with a mass given here. Okay, so just a minute. So number A19, we're given an equation. This is the equation that we're having here. So the equation, they're saying, what is the correct nest equation for this expression given here? The nest equation is simply going to be, so this is, the nest equation is just equal to the E cell at standard conditions minus you have RT over the number of electrons, Faraday's constant, then ln or log, depending on the base you are using. We say Q, where Q is a ratio of the products over reactants. So products over reactants. So in this case, we're just having, if we do our replacements, we don't have the E cell. We'll just say the E cell of the conversion of M2 to M. That's what we're having, minus. This is going to be R. We use 8.3145. The temperature is 273 plus 45. So 273 plus a 45. This is 8. This is going to be 1. That's 3. So that's 318.15 because there's a 1 5 there. Then down, we just have 2 electrons. The Faraday's constant. The Faraday's constant F is given to be this guy here. So that's what we are having. So this is what's going to be 96485. Then we have log K. So K is the quotient. So we're just going to say, when we punch this whole thing, we are getting 0.01371. Then you're going to have log, the base is 10. When you just put log, meaning the base is 10. This is 1 over m2 plus. This is what you get. So this is supposed to be our answer. But if we take it to be, if we take this guy to be just m, meaning this guy here is going to be positive. So no wonder here on the answers, the only probable one that we can have is the only likely one here. I said D earlier on because it's the closest, because we're having this. And then the only reason why this changes to positive is because of the ratio we've done this side on the 1 over m to the power 2. Yeah, because we can actually change this. This can be changed. Yeah, so this can just be rewritten. I can show you here your indices. This can be rewritten as, we can write this as E cell 0. There's a negative there, 0.1371. Then this is log 10. This is m2 plus with the power -1. The -1 can come down, and then this becomes positive. So it can become like this. But there's a separate video that just explains the whole topic. So you may try to watch, or you should try to watch everything so that you get a glimpse of where this whole thing is coming from. Then the last question, they're asking for the value of G if the reaction is non-spontaneous. So if the reaction is non-spontaneous, our E cell is always going to be less than 0. Then we know G, delta G is negative N, F, then E. Yeah, so if this is negative, negative, and negative, that is going to give us positive, meaning G will end up being bigger than 0. G is the work done whenever the reaction is non-spontaneous, because now we're using electric energy to produce chemical energy. So we're using electricity to generate chemical energy. So we need the help of electricity. It's like when you're charging your phone. So there's a typical nice example I gave in the video. So to explain why G is positive. So this is your answer for A19. Yeah, then we go to section B. So section B, B1, they are saying a piece of antimony with a mass of 17.41 gram is submerged in 46.3 cubic centimeters of water in a graduated cylinder. The water level increases to this. Calculate the density of the antimony to the correct number of significant figures. So they want the density, right? So you just find the difference between, so this is the water, this is the volume of the water before it was submerged, this is the water level after it was submerged. So you just find the difference between the two volumes. You have a 48.9 minus a 46.3, the answer is 2.6, and then you know density is equal to mass over what? Over volume. The volume is 2.6 cubic centimeters. So when you divide this guy, 17.41, that's how you get the 6.69. The reason why we are leaving it to 2 decimal places is because or rather 3 significant figures. So the least significant figure in the data given, the data values given was 3. So that's why we're leaving it to 3. This is going to be your answer. That's a 6.69 grams per cubic centimeters. The number B2, they're saying naturally occurring ion contains, these are the percentages that you're having, these are the isotopes that you have. The respective atomic masses are the following. Calculate the average atomic mass of ion. So the formula here, I'll give it to you. So this is B2. So question B2, they have given us the percentages of each isotope. That's what we are given. And we're also given the respective atomic masses. So we're going to multiply the respective atomic masses. So here we're given a 53.9440. Then here we have the 55.935. So we're just going to multiply everything by their respective. This is 56.9 935. Then same applies here. We're multiplying this with a 57.933. So you multiply this, so this is the percentage, that's your P1, then this is your A1, the isotopic atomic mass. So when you punch everything, so I'll just write the first part, 9 this, multiplying the percentage, then plus, there's a 55,955, multiplying 91.66. So when you are done punching everything, then divide everything by 100. That will give you your answer. Yeah, so the answer there should be, the answer is going to be in AMU as well. So let me just punch this directly here. That's a 53.940 multiplying a 5.82, then plus we're having a 55.955 times 91.66, then plus we're having a 2.19 times a 56.935, then plus we're having a 57.953, then times 0.33, then everything divided by 100. So this is divided by 100. So the answer I'm getting is a 55.83. This is AMU, that is going to be the atomic mass unit. So this is supposed to be the answer of B2. Yeah, so that was supposed to be the answer here. Yeah, so you needed to write it as 55.883 AMU. That's what you get. That's the average mass. Then B3, they are telling us to say a gas contains this pressure, 78.5 atm of nitrogen, and you have the 998.7 atm of oxygen and 324.1 atm of hydrogen. Determine the total pressure of this gas. So the total pressure of the whole gas, we're just going to sum up the 78.5, then plus the 998.7, then plus the 324.1. So the total is just going to give us this answer that he got here, this based on the one of the script. So that's the total. The total pressure is just equal to the individual partial pressures, the partial pressure of nitrogen, the one for oxygen, and the one for hydrogen. It will give you the total pressure. That's your question B. That's your B3. So like I said, the question are jumbled. So even in the document, for those that are in the WhatsApp group that I shared, you will see that the document also, the questions, they are jumbled. So now we're supposed to go on question B4. Yeah, so for tuitions or to be added to the WhatsApp group, for those that are just accessing the online session without having access to WhatsApp interactions, you can simply WhatsApp me on this number. This is the number you can contact me on, or if I say anything that's contradicting to what you learned in class, or you just need clarification, you can just feel free to WhatsApp me. Then here we're having number 4. We're saying convert 2.2 atm to millimeter mercury. So we want to convert this. This is 2.3. On the unit conversion here, they told us to say 1 atm is equal to 760. This, they gave you this, and we're trying to convert 2.3, right? So we're just saying 1 atm is simply the same as 760 millimeter mercury, micrometer mercury. So we're having 2.3. This is that. We're having that. So we do the cross multiplication. 2.3 by 760. This should give us, according to the unit, this is 760. So we should get, this is the answer that we are getting, 1748. This is what you get. Then they're saying, what is the molecular geometry of BF2? So BF2, we look at beryllium. How do you get the correct shape? Look at beryllium, that's Be. So beryllium is here, that's with 4 electrons. It has two electrons in the outermost shell because it's in group 2. It's a metal, right? Is it Be? So according to our question here, this is beryllium. Then fluorine. So fluorine is going to have, so let's say we have each fluorine is this side, right? Let's say we're sharing an electron. This is Be. These guys are sharing an electron. So fluorine is happy. Another fluorine is happy. We fill in this side. We fill in this side. Yeah, so this is going to be linear. So this is correct because there are no lone pairs here. And to maximize the repulsions, these attached atoms of fluorine will both be at an angle of 180 away from each other. So the shape is simply going to give us a linear. That's what we get. Then number B6, they are saying what is the hybridization state of carbon A, this carbon here, in the following organic molecule. So carbon is related to sp. I mean, there's a triple bond here, so the hybridization here is just sp hybridization, because remember we said under hybridization, whenever you see a single bond, it's sp3. Whenever you see a double bond, it's sp2. Whenever you see a triple bond, it's sp. And if you see a combination like this carbon that they're asking us, it has a single bond and a double bond. We respect the triple bond more than the single bond, and we respect the double bond more than the single bond. So this is the order of priority that we follow. This is more respected, followed by that, then followed by that. Yeah, so if they are pairing in the same molecule, the triple bond is more dominant than the single bond. So the overall hybridization is just going to be sp hybridization. Yeah, so this is what you have. Hope this is okay. There's a separate video again that just talks about hybridization. Look at number B7. They're saying this is under atomic structure. Calculate the length associated with a 2-gram golf ball traveling at a speed of 5 meters per hour. So we are going to use the wavelength. This is the de Breugle's equation. Planck's constant is the mass and the velocity. It's the only equation where V means velocity. So we are going to convert the velocity, which is 5 meters per hour, into this is going to be 36, right? Because every hour has this seconds. So we're going to say 5 divided by 3,600. So this is the same as in seconds. So our velocity, I mean in meters per second, it's the same as 1 over 720 meters per second, or rather in decimals, 0. I can write it in scientific. It's the same as 1 point. This is 1.39 times 10 to the power 123 negative 3. So that's the speed that we're having. Then the mass has to be in grams, so this is going to be 0.123. That's 0.2 kg. Yeah, so to solve our question here, number B7, we're just saying de Breugle's equation is equal to Planck's constant. This is negative 34 over the mass, which is 0.2. The speed, which is just going to be a 1 over 720. That's what you have. Then we're just going to punch everything there. So this is joules second. This is in kg. Then this here is meters per second. We're looking for wavelength. The answer has to be in meters by the time we are done, because seconds will cancel. Joule is the same as meters. What? It was the same as this, right? It's the same as this. Kg, right? It's the same as this. Meters per second. Yeah, so we're saying this is what you get. Yeah. So here you're going to divide. So we're saying 6.626 times 10 to the power negative 34. That's the Planck's constant. Divided it by, we're having 0.2 times 1 over 720. Okay, so I'm just saying 0.2 times 1 over 720. That's the answer. Then multiplied by the times 10 to the power negative 34. Okay, so according to my answer here, I'm getting a 2.39 times 10 to the power negative 30 meters. Yeah, so this is going to be a wavelength. That's what you get here as your wavelength. Yeah, this is 2.38 times 10 to the power negative. There's a 9 because the 5 can give this. This is what you get, or here, I mean on B7, sorry. This is the answer for B7. We use de Breugle's equation. That's what we get. Yeah, so this is 239, 10 to the power negative 30. This is meters. That's the wavelength. Then look at the next one. Yeah, so the next one here, they are simply saying an electron in a certain atom is in n is equal to 2 quantum level. List the possible values of L that it can have. So when n is equal to 2, we just go back here. This is B8, one question B8. Yeah, so B8 is simply testing our quantum number knowledge. So B8, when n is equal to 2, what will be the L values? Just 0, 1. The S orbital and the P orbital, right? That's basically what you can get. The ML values depends on the L value. So when L is equal to that, you get that. When L is equal to 1, the ML values will be -1, 0, and +1. So I hope this is okay. They just want this. So L, you write, is 1 and 0. So these are the only answers that are needed there on B8. Then number 9. So B9 is under electrochemistry. They are saying 2 half-cell reactions of an electrochemical cell are given below. This is what you're having. Write the balanced redox equation for the 2 half reactions. So you look at the 2 reactions that you are given, then you see that the electrons are not balanced, right? So we're going to balance the electrons by multiplying this first one by 2, this second one by 5, so that we balance the electrons. That's what we have. So the balancing of the electrons won't affect the electrode potentials that you are able to see at the end. So here you had, let me write this, there's M. This is what you're having. There are 8 hydrogens and 5 electrons. So the reason why I'm only focusing on the electrons is because everything else is balanced. Yeah, so there are 4 water molecules. Then the value here of the E cell is 1.51 volts. And the next equation is the one for this guy here to give us 4. This is 4 positive, then plus 2 electrons. The voltage here is 0.15 volts. So now, like I was saying, this is like us trying to get rid of electrons, balancing simultaneous equations. So I'm getting the number in front of electrons in the first equation and multiply the second equation and get this number 2 to multiply with the first equation. This will give us something like a 2. This is what you're going to get. This will be 16 hydrogens. This will be 10 electrons. This will give us 2 Mn2 plus. This will give us 8 water molecules. The value here is unchanged. It still remains the same. Then here you're going to get a 5 SN2 plus. This is giving us a 20 SN4 plus. Then plus a 10 electrons. This is 0.15 volts. Then from here you are seeing that the electrons can cancel out. So if the electrons can cancel, so here the electrons are on opposite sides. So meaning when we cancel, we just add up everything. This is going to be 2, the permanganate with a negative, plus 16 hydrogens, then plus this guy here, everything on the reactant side. There's a 5, this is a 5, then SN2 plus, then this gives us 2 manganese plus, we have 8 water molecules, plus 20 SN4 plus. Then we add the values here. So the cell potential as well is equal to, this is going to be a 6, 6, then 0.1. So this is the voltage that we're having. So we have given them the balanced equation and the cell potential. That's basically what we have. Yeah, so this is going to be the final answer. The reason why we're just adding these two without reversing anything is because the electrons are on opposite sides. That's the reason why we're just adding them. If the electrons were on the same side, we would have reversed the one that would have had the smaller cell potential this side. Yeah, that's what we would have done. But here, it's already in a proper way. One is a reduction, one is an oxidation expression. So now we're just summing them up. So now question B10. B10, they're saying a galvanic cell consists of magnesium electrode with the concentration 1 molarity solution and a silver electrode in 1 molarity. They are giving us the concentration to be the same, so this is under standard conditions. You are given the silver nitrate. Calculate the standard electromotive force of this cell at 25 degrees Celsius, given that the electrode potential for the silver is this, then for the magnesium is simply this. So we're supposed to write two separate equations electrochemical equations that are simply going to help us to get the E cell. So to do that, we'll write it here. We'll split it. This is going to be, let me show you how we're going to be splitting it. This is the electrode potential for the silver changing. This is silver ion changing to give us the silver solid, which is equal to the 0.8. This means that the energy, or rather the voltage needed to convert, so this is positive 1, so it needs 1 electron for it to become this. The voltage needed is 0.8 volts. That's what is implied by this. Then again, when they say the electrode potential for the conversion of magnesium 2+ to magnesium solid is given as negative 2.36, meaning to convert magnesium 2+, we need 2 electrons, of course, to form this guy. The voltage is negative 2.36. We can balance the electrons by multiplying the first one by 2. So we know if we multiply this by 2, it won't affect the value of the E cell. So now you see that the electrons are on the same side. We can't just add these two equations because the electrons won't be able to cancel. So we reverse the one that has a smaller voltage. So this equation is going to be known as the anode because it has a less voltage this side. Automatically this one becomes your cathode. So we reverse this one, meaning what was on the product side becomes the reactant. So it's going to be M. Magnesium solid is equal to magnesium 2+ with 2 electrons. The value changes. This is the only time where the voltage is affected when you reverse an equation. Then here the top guy is still the same. The top equation is still going to be the same. This is 2Ag. This is 0.8 volts. So here now we can add. By addition, we're going to cancel the 2 electrons appearing on both ends. This will give us manganese solid. If there is no charge, meaning it's a solid because it's a metal, right? Then this is in aqueous. This is giving us manganese 2+. This is in aqueous. Then this is silver. This is solid. Then the E cell is just going to be equal. We add these two, so we're going to get a 6, 8, 9, 10, 11. That's 1. Then that's going to be 3. So the voltage is this. Since the answer we're getting is positive, meaning this is happening in a galvanic cell and the reaction is spontaneous, so this should be added. You need to add this. It shows that you understand what you're doing. So that should have been the answer to B10, the last question on section B. Now section C here, they're giving us, they're saying answer all questions. C1 carries 10 marks and the other questions carry 5 marks each. So question 1 is a titration experiment. They're giving us to say a student performs a titration to determine the concentration of 1 liter solution of sulfuric acid. 10 milliliters of this solution is transferred to a 100 milliliters volumetric flask and diluted with diluted with distilled water. Meaning we put the water until we hit the 100 milliliters mark. Then we get 25 aliquots of this, meaning we're going to have 4 solutions, 4 samples, right? Diluted are titrated with 0.1 mole per liter solution of sodium hydrogen carbonate. The average titer volume is given. So they've given us the volume of the minimum volume that is needed, the average, the mean titer. So you are going to say, they're saying the balanced chemical equation is given like this. They are saying calculate the number of moles of sodium hydrogen carbonate in the solution. So we already have the volume. The volume, they've given us the average. The average volume given is the one for the sodium hydrogen carbonate. The concentration is here. The problem with this question is that when you get the first answer wrong, everything else becomes wrong. Yeah, that's the reason why this person here was marked incorrect or wrongly here. I mean, they just cancelled because once you get the first answer to be wrong, everything is wrong. So we are given the concentration of the sodium hydrogen carbonate and the mean titer volume, meaning we can say number of moles is equal to concentration times volume. The concentration is 0.1. This is mole per liter. I need to show you units. The volume is 33.40 milliliters. We convert this to liters, divided by 1,000 is going to be this 40, this is going to be liters. Then you multiply, this is 0.1 by 0.0334. When you convert this, the answer you are getting, your moles, as 0.033, then 4 moles. So these are the moles for the first answer. There will be the moles you will be using to do your mole ratios, because once you get your 0.00, this is 334, these are the moles. We can do the mole ratio because these are in a ratio of what? 1 to 2. So we divide this by 2, get the moles of this guy. So the moles of this guy, the sulfuric acid, these are in a ratio of 1 to 2. You are seeing there's a 1 here, there's a 2 there. So meaning we're just going to divide this by 2. So the answer just divided by 2. Yeah, so this will be 0.00167. That is what you needed here. Then for the next one, they are saying calculate the concentration of sulfuric acid. You do have the number of moles of sulfuric acid, and you also have the number, you have the volume. The volume is this, right? That's the 1 liter that you have. So you have 1 liter, which was diluted and everything else, but calculate the concentration of sulfuric acid. So this is in the 25, because the aliquots that we're using were 25 milliliters. So the concentration will be number of moles over volume. The number of moles, 0.00167 divided by, so here, let me just show it properly here. We did more ratios, first of all. We did more ratios. More ratio, we said there is 1 to 2. We don't have this. Then here we had 0.0. This was 0.0334. Yeah, that's how we got the X. The X to be the number of moles of the sulfuric acid. Is it this? The sulfuric acid, let me just see this. This is H. Yeah, there's a 2 there. So this is 0. When we divide it by 2, we got 0.0167. This is the moles. Then, so this will be the number of moles for the sulfuric acid in the 25, in the aliquot that we're using. So the question that follows next here is asking us to calculate. They're saying calculate the number of moles of this. We've gotten the number of moles. Then they're asking for the concentration. So the concentration is simply going to be over the volume. The volume is just 25 mils. So we'll divide this by by 1,000. So this is going to be 0.025. So this will give us 0.00167 divided by 0.025. So we're getting the concentration to be 0.668. This is the concentration that we are getting for the sulfuric acid. Now, if this is the concentration in the aliquot, we need the concentration in the actual original thing, which had 1 liter. So this was in the 0.025. So if 0.025 liters gave us 0.0668 molarity, 1 liter will be equal to what? So this is going to be the expression that we're going to solve. So again, we'll divide. This is going to be, yeah, so we're multiplying the concentration by 1, then dividing it by the volume. Yeah, so this is going to be 0.0668 divided by 0.025 again. Yeah, so this is giving us 2x. Here you will get a 2.672. This is the molarity in the original sample. So this is what you're supposed to be getting. Then once you get this, because this is according to our question, the initial volume is having the 1 liter. So that's the reason why we're using this, right? Yeah, so if anything, we're supposed to actually get from the 25 aliquot that was diluted, then back into the 10 mils, then back into the 1 liter. It's like we sampled this thing 3 times. So it was in the 1 liter. In the 1 liter, we got 10 mils. So in the 10 mils, after we got 10 mils, we then diluted these 10 mils to 100, right? By adding water. Then from the 100 mils that we diluted, we only got 25 mils. Yeah, so no wonder we're going back like this. Yeah, so I hope this makes sense. Then the last question here, they're saying, calculate the percentage uncertainty of 250 cubic centimeters volumetric flask with the uncertainty of this. So here we just have to do this guy over the this is supposed to be 0.2 divided by 250, then times 100. Yeah, so this is supposed to be over 250, then times cubic centimeters times 100%. Yeah, so they want the percentage in uncertainty in this form, so this is going to give us 0.08%. This is the uncertainty that we are having. So this is what we're getting. So this is how we're supposed to do number B. Then now we need to go to B2. So let me just scroll back. Like I said, the questions are a bit jumbled because of how the document was scanned. So C2, they're telling us to say if it takes 1.25 minutes for 0.01 moles of helium to effuse, how long will it take for the same amount of ethane to effuse? So this is under the rate of effusion. This is simply testing whether you remember what you did under effusion. So we're simply going to start by writing the formula first. Yeah, so you can pause the video. This is under gases, so try to redo it first alone before you play the video. So the formula here is supposed to be a comparison between helium and ethane. So we're having the time given. They're giving us the time for helium. So we have, so first and foremost, we're given the time for the helium effusion, and we're given the number of moles. Then the question says, if it takes 1.25 minutes for the 0.01 moles of helium to effuse, how long will it take for the same amount of ethane to effuse? So same amount means the number of moles is the same, so we'll just have to use the time here. We're saying we don't know the time for ethane, but we know to say the time for helium is 1.25 minutes. Then we know to say the mixture of helium, according to our periodic table, helium is here, that's a 4, so we'll just put a 4. So this is going to be 4 grams per mole. Then for ethane, we'll have to calculate this. This is just 6, then this is going to be 24, that's a 30. So meaning we have this. Now if we calculate the value of x here to be 1.25 minutes, then multiplying, this is 4 over 30. So here we can get our answer. We're saying 4 divided by 30, then square root the answer you've gotten, then multiply it by 1.25, which is simply going to give us a 0.45. This is what I'm getting here. 6, this is simply what I'm getting. Yeah, so they're saying ethane, this is what you're getting. So according to this, they're saying how long will it take for the same amount of ethane to effuse? So if they're the same amount, meaning the moles are the same like the way we've done it, then we're just using the time, right? The time is 1.25. That's the time for ethane. So ethane is that, and we're having, ethane is this number that we've gotten here. So according to the data given, this will be your solution. This is how you are supposed to do it, because unless if I've done it wrong, but for the mixture, the carbon is 12, hydrogen is what? This is, I'm just going to take it as 1 because of the 1 there. So that's a reason why on the question there we have 6 hydrogen. So 6 plus what? 2 times 12, that's a 24, right? That's a 30. Then for the helium, we're having a 4. So that's basically what we do. Remember that says the rate. So here I didn't use the actual rate where we had to divide the time. I put the time in seconds and then divide by the number of moles, because they said the amount is the same. So I won't have to go through all that. So we just have to use these ratios here. So this will be your computation. This is what you're supposed to get according to the data, though it's not logical because the time here was supposed to be more. It should have taken more time for ethane to effuse. as compared to helium, because ethane is heavy. It has 30 grams per mole, whereas helium has 4 grams per mole. So it should have taken more time. Yeah, so this is what you have according to the question. Please feel free to WhatsApp me in case this is confusing, or there's a simpler way or an alternative way that you feel this should have been done. Yeah, this is the WhatsApp number you can contact me on. So the next question is on number C3. Yeah, so C3 is simply asking us to get the empirical formula. So here I'll just do this straightforward. So the empirical formula here, this was partially correct, but then the person got 3 marks. Why? So because of the representation. Also, if we take the phosphorus, the percentages, so we put them underneath here, this is what you get. Then we have the oxygen there, the 56.36, divide by the misters from the periodic table. So if you divide by that, so he got these small numbers here, right? Let's assume this is what he got. This is what we all get, this is 225. Here we divide by the smallest, right? 122, then even here 124, 122. Then here you get 1, then this is going to be here, lastly here, you're supposed to get the number that he's getting. So if I divide this, that's 3.5225 divided by 1. That's 4.122. 3.5225 divided by, that's 1.4122. So the answer here that he's getting is a 2.49, which can be written as 2.5. Now the number here is the same as, so if I may just write this in a fraction form, it's the same as 2/3. So to get rid of the 2 down here, I'll multiply everything by 2. So this will end up being 2,3. So this was supposed to be P2 and O3. This was supposed to be the formula. That's the reason why he only scored the 3 instead of totalizing it to get a 5/5. So yeah, this is the reason, because of this part there. So this is what you get. This will be our empirical formula, P2O3. Yeah, that will be the empirical formula for C3. And for number 4, they are saying using shorthand notation, write the configuration of copper 2. Okay, so copper has what? Is it a 24 or 29? Okay, 29 from our periodic table. So we know that copper, going backward like this, the first thing that we find here, the noble gas we find is argon. Argon has 18. So the structure of argon, this is C4. Argon initially has 1s2, 2s2, then 2p6, then we have 3s2, you have 3p6, you have 4s2. So this is argon, 18, right? 18 electrons. So we're just saying copper 2 plus is the same as argon. Then this is argon, right? Then we come here, we say 4s2. We need to say 3d. 3d what? 3d, this is supposed to be 1 here. This is supposed to be 10. Remember, we said copper and chromium are the exceptions. Would rather fill up the 3d and leave the 4s to be half filled. That's what we have. Yeah, so now we're just saying this would have been the configuration 18, 19, 20, then you get 29, right? So they've removed 2 electrons. This is just for copper without the charge. This is copper. Now if they remove 2 electrons, it simply means they remove 1 there and 1 there. So this will just be, you can write it like this. Some people just say this, 3d9. This is the answer to our question here. Yeah, that's the answer that they want. So here the answer should have been argon, the shorthand, argon 4s0 and 3d9, because there's a 2 there, meaning they got 2. Indicate which of the following species, indicate which one of the 2 species in each of the following pairs is smaller. So which one is smaller between the 2? So this guy is smaller because we gain an electron, right? Becomes bigger for nonmetals. And here the smaller one is this guy because it lost an electron. So for metals, they become smaller as they lose electrons. So the original thing for metals, the original thing is bigger than the second thing you get. It's bigger than the other guy because electrons are being removed. Then for non-metals, they always increase. So this is less than this, then this is less than that because we are adding electrons. Yeah, so this is what you get. Then number C, arrange the following in the order of the increasing first ionization energy. So ionization energy increases from left to right. So we have this. So the order that he made here is true, because if we go back on our periodic table, we're having, so the order there is asking us to compare what we have. Sodium, so there's sodium. Let me just show us here. Let me just erase this. So we're having sodium there. There's a sodium. There's aluminium, right? Then there is chlorine. Is it? There's chlorine somewhere there. Then there's S, right? So there's S. So the increasing order should be this guy here comes first, followed by that, followed by S, then followed by chlorine at the end. It increases like this. So now we just follow them the way they are in the period. Yep. So that gives us our C4, number C. Then we can go to number C5. So number C5 here, they're saying what is the bond angle for boron trihydride. So this guy here is just going to be boron. There's this here. So there's a hydrogen, there's a hydrogen, there's a hydrogen. There's no lone pair on this guy. So meaning these are supposed to be all equal. So 360 by 3, that's going to give us 120. So that's the angle, the bond angle here. That's what they want. Then here they're saying answer the following question based on xenon tetrafluoride. So what's the lowest structure of this? So here, xenon, we can just go on the periodic table. We check the lowest. We check the valence electrons for xenon. So fluorine already know it's 7, but then xenon, which group does this guy come from? So let me just show up the periodic table here. So xenon, that's Xe. So xenon is somewhere there, okay, which is a noble gas with a okay, so meaning it has 8. Is it 8 in the outermost shell? So let me just check. So this is okay. So we are saying we have xenon has 8 electrons in the outermost shell, so we can just write it here. Yeah, so xenon has 8 valence electrons. We can just write that. Fluorine, each has 7. Yeah, so there are 4 of them, right? So each has 7. Each fluorine atom has 7. So we're just saying 7 by 4. This is going to give us what? 28. 28 plus this. This is going to give us 36 electrons in total. So xenon is going to be on the middle. We put our xenon right here. We satisfy this. So by now you know how to write the Lewis structure. So I'll just go direct. So this is a single bond. Provided the attached atoms are happy with obeying the octet rule, we don't really care what happens to the central atom. This is 888, so this is going to be a 32. We're remaining with 4 more electrons, so we'll put the lone pairs there. So this is going to be the Lewis structure. That's what you have. Then how many bond pairs and lone pairs are there? So there are 4 bond pairs. That's what you have. Then there are 2 lone pairs. Yeah, so this is correct, what he wrote here. Then number 6, they are saying calculate the standard free energy change for the following reaction. This is what you're having. So in this case where we're given concentrations, we need to first of all dismantle this reaction, this guy here. We're asking for the free energy. We're looking for delta G. That's what we're looking for, right? Delta G is NF, then the E cell. So we need to get the E cell first. So this is a very long process. So I'll just go straight forward here, and I'll just start here to say we have this question. Is it C6? That's our C6. So I'll rewrite. So ignore this balanced equation. This is just telling you to say the experiment is happening at standard conditions because we are having the common solution throughout. You are seeing one molarity, the molarity is the same throughout. So we are going to write the expression like this because this is under standard conditions. So we are having the first one, which is just going to give us, we are breaking it down. So this is C6. okay. So let me just say we are having the first guy is there's AU here. This is 3 plus. Then there's AU there, if I'm not mistaken. Then the voltage here is given to be 1.5 volts. So meaning AU3 plus is gaining 3 electrons to become AU. Then this is 1.50 volts. Then for the other guy, this is just the same as calcium. So I'm just going to write it directly here. Calcium with what? 2 electrons. Gaining this to become calcium. This is negative 2.87 volts. So from here, we can balance the electrons by multiplying this by 2 and multiplying this by 3. Just swap the integers in front. And remember, we said the numbers you are using will never affect the voltages. They just affect what you have in terms of the equation. It will never affect these guys here. So it will just be 2 AU 3 plus. This is 6 electrons to give us 2 AU. This is 1.5. Then here we're just having 3 calcium 2 plus. This is the 6 electrons to give us 3 calcium. Then this is going to be negative 2.87 volts. Then we can reverse after we identify the second one to be our anode. We say the one that always has a smaller voltage is always going to be your anode all the time, because it's easy to convince it to lose electrons. So we flip it. It's going to be 3 calcium. This is going to be 3 calcium 2 plus. Then this is 6 electrons. The value now changes and becomes positive. Then here we are still going to have 2. This is gold or something. This is 2 AU. This is gold 1.5 volts. So now we are able to cancel through the electrons because they're the same. This is just to help us to get the balanced equation. So this is how they got that equation that you have. The concentration is 1 molar because it's in aqueous. This is 1 molarity, then plus 2 AU. This is how they got that equation. The E cell, we need to get it. So we're adding these two. So that's a 2.87 plus a 1.50. So I'm getting a 4.37. That's what I'm getting to be my voltage. Now they're asking for free energy. Free energy is equal to negative N. The number of electrons that you cancelled, that doesn't appear in both equations. So this is the number of electrons is 6. Faraday's constant is 96485. It's given there. Then here we have 4.37. So meaning that Gibbs free energy is just going to be 96485 and by 6. So the answer here is giving me a 2.53, then by 10 to the power, that's going to be 1, 2, 3, 4, 5, 6. That's 6. It's joules. This guy is in joules. So this is what you get, and it's negative. So this is basically what they wanted. This is the answer that you have. So this is going to be the answer for this question there. Hope this is okay. Then the last question now, C7. They're saying calculate the equilibrium constant for the following reaction. This is what we're having. So the equilibrium constant here, it's simply going to be, we're looking for the E cell. So this is the E cell. We know to say the one at non-standard conditions, we say we have the E cell is equal to RT, then we have, this is NF, then we have ln, the value of K. We're looking for K. That's what we're interested in. So you can get the E cell in a similar way that we got the previous one. So for this case, we will reverse this guy. I'll just get the E cell. So you can attempt this. You can, the same thing that we're from doing on C6, you can do the same to get your E cell. So according to my calculations here, my E cell is just going to be 0.14 plus 0.15. So my E cell is 0.29. So please, if this is confusing, like I've said over and over again, there's a separate video that will explain to you the whole topic so that you're able to understand the concept. Then R, we're going to use 8.3145. The R that we use is this one that doesn't have pressure units. There is no pressure here in this universal gas constant. The others have like pressure is pascals. bars, ATM, tar, or millimeter per mercury. So we're just using the first one because there's no pressure mentioned, right? So this is what we're going to do there. Then the T, the temperature is 25, so we're just adding 25 plus 273.15. This is a 298, 298.1, this guy here. The number of electrons, if you just look at this, this is 2, and that's going to be 2. So the number of electrons is 2. The Faraday's constant is 96485. We're looking for ln K, right? So now we're going to just do cross multiplication, which is 0.29 times the 2 down times the 96485. So this here is the same as 55961.3 is equal to 8.3145. Multiplying it by 298.15, then ln K. We divide both sides, so ln K is equal to, so this divided by 8.3145 times the 298.15. So I'm getting a 22. This is what you have, 22.57. We're trying to get the value of K, so I introduce E this side and E this side, meaning this will cancel. K is equal to E to the power 22.7, so I'm just going to say shift E, my answer. This is going to give us K is equal to this number here. This is a 3, this is a 672. Yeah, so it's a very big number that you get there. So I'm just going to write it as 6. This is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be 10 times 10. I'll say 6.4 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9. So this is a constant. So generally this is how the test is supposed to be, and you have to be ready for all the 3 sections, having all the topics on your fingertips. So now this marks the end of this discussion. This is meant to just help you solidify all the principles that you've learned. If you do have any questions, you can please feel free to contact me on WhatsApp so that I recommend a video in case you are not you are not understanding anything that we're doing. You are failing to understand some portions that we're discussing because you lack the background information of a topic. I can recommend to you a video that will be helpful. Yeah, so thank you so much for watching.